Dear audience, we have here radio waves and noise in communication systems. It is extremely important to consider noise while designing communication systems. If the noise level is comparable, for example, in the extreme case is comparable to the signal level, then the signal will not be distinguished. The signal will not be useful. We have the thermal noise. We have the thermal noise, or called also Johnson noise or Nyquist noise, is caused by the random motion of electrons in a resistor. We have a resistor here, R, and due to the random motion of electrons, there would be a voltage, instantaneous voltage, random voltage here between the terminals of the resistor without a source, because the thermal noise itself will be like that. As you can see, the average value of the noise, thermal noise, is 0, but it has power, of course. The root mean square value is given by this equation here, 4 kTr delta F under square root. K is Boltzmann constant, given by this value, Boltzmann constant given by this value. Okay, given by this value. (1.38 10⁻23 joule per Kelvin), and T is the absolute temperature in degrees Kelvin, R is the resistor value in ohms, and delta F is the frequency bandwidth considered. This is the root mean square value of the thermal noise. Now consider a resistor connected to a network with input impedance of an input. And this is a resistor connected to a network. That's the network. The resistor value is R, ohms, and the input impedance is here Z input. Or if it is for simplicity, let's consider it to be here Z input equal R input. So there is complete matching or full match between the resistor and the network. Now the power, as you know, the power the power is equal to the voltage divided by the current, and the voltage developed here is the so it is the if you want to calculate the power, we calculate it as I squared times I is this power N, noise power delivered to the network is equal I, the current squared, times the input resistance. R input equal R, so we put R here, or R input. Now the current is equal the voltage developed by the resistor, which is I squared is equal V noise of the resistor over the total impedance. R plus R is 2R here, it will be 2R, or R input, they have the same value, all squared times R input, which is also R. This is equal to V noise squared. This is 4R squared and this is R, so we will have here 4R. We have here 4R, as we can see in this equation, V noise squared over 4R. Now V noise squared from this equation, if you square this equation, the square root will disappear and you will have 4 kTR delta F. Divide 4 kTR delta F by 4R, the 4 will go, the R will go, and you will have KT delta F. So this is KT delta F. This is the maximum noise power that a noisy resistor can deliver to a network connected to it. Of course, when there is complete matching. If there is mismatch, the power will be less than that. So it is KT delta F. This is the maximum noise power that a noisy resistor can deliver to a network. Now, if we want to calculate or to find the equivalent noise temperature, we divide the noise power by K delta F, and we will obtain the equivalent temperature. It is P noise power KT delta F over delta K delta F. You will obtain T. This is simple here, but in other cases it is not as simple as that. Communication systems involve not only resistors, it involves resistors, amplifiers, mixers, transmission lines, antennas, etc., etc. So we will consider these elements. Here we consider an amplifier with a gain of A and noise figure of F. The source here is Vs, and the resistance, internal resistance of the source is R at temperature T0. And here we consider also the amplifier to be at temperature T0, also the same temperature T0. And the input impedance to be R, complete matching. We will calculate here the noise figure. Noise figure is by definition the signal to noise at the input divided by the signal to noise at the output. The signal at the input, let's call it PSI. The output signal will be simply the multiplication of I. This is power gain. Here, power gain. A times the input signal, you will get the output signal. So A PSI is P output. Now the maximum input power deliverable to the amplifier, which is here maximum because we have matching, we have already derived that. It is KT delta F. Here, KT delta F. You put it here, KT delta F. This is signal noise input. input noise, NI, noise input. And this is signal input, and this is signal output. This is S output. Okay. Now the noise output is the signal, it is the noise power from the resistor multiplied by the gain A. So it is KT delta F times the gain A, plus the noise power added by the, or generated by the amplifier itself. Let's call it P and A. Now this is equal to, here, PSI. If you can cancel this with this, and you will have 1 over A. 1 over A. This will be in the numerator. You will have A K T naught delta F, A K T naught delta F plus P and A, plus P and A, the noise of the amplifier generated by the amplifier itself, and this will be in the denominator. This will be K T naught and delta F. You can see that we have A K T naught delta F, A K T naught delta F. So this will cancel with this. Can put, if you want to, can cancel this and put it here, A here. So this is equal to this. This over this is 1 here. Okay. And plus P and A over this value, A K T naught delta F. If you subtract F 1 from F, it will be F minus 1, and you multiply by this, you will obtain P and A. So this is, we multiply A K T naught delta. So this is the noise power contributed by the amplifier with a noise figure F referred to the output as the output. If we want P and A as the input, we just remove, we only remove A. Now so P and A as the input will be the same as this. It will be F minus 1 K T naught delta F without A. If you want the system temperature or noise equivalent temperature for the amplifier, we divide by K delta F, and we will get F minus 1 times T naught here. So it is F minus 1 T naught, the equivalent noise temperature of the amplifier. It is the equivalent temperature of a resistor as the input. That gives the same noise power as the output. Here we consider the mismatched case. We have V generator, Z generator, internal impedance at temperature T, and we consider here the amplifier to be at different temperature of T naught. We consider here the temperature to be T naught, and we consider the resistor to be at, or the impedance here to be at T. There is mismatch here. Zg does not in general equal to Z input, and the power gain again is here, and the the noise figure is F. Z input equal in general R input plus Jx input, and also Zg is equal Rg plus Jxg. Now P input is equal I squared magnitude times R input. This is the real power delivered to the amplifier. So this is I squared times R input. I is the voltage. I squared equal V squared over impedance squared magnitude. V squared is from this equation. You can see from the resistor is given by this equation. V squared, you cancel the 1/2, it will be 4 kTr delta F. This is V squared. V squared is equal 4. R is Rg, of course, the real part of the generator impedance. Kt delta F. This is the V squared, V no squared from the resistor of the impedance here. Now the impedance squared is Zg because they are in series. When you look here to here, Zg and Z input are in series as seen by the source. So Zg plus Z input all squared times the real part R input to obtain the real. Now this is equal to K, if you consider K, T delta F, if you take it alone here, KT delta F, the original value. If you take KT delta F here, as you can see, let's call the remaining part M, the mismatch factor. It is M is equal 4G R input here over Zg plus Z input all squared. This is the mismatch factor. Now this is to calculate the we want to find the noise figure for this here, when there is mismatch. Now we need P noise input, we need also P signal input. The input signal delivered by the source to the amplifier is equal again also the current squared times R input, but the current here is generated by the generator, not by the noise. So it's V generator over the total impedance with Zg plus the input all squared. This will give I squared times the real part, which is R input here. We do not need to derive this because this will be the same. Instead of the input noise power, we put here the input signal power times the mismatch factor. Input signal power is Vg squared over 4G, because we will have the voltage here is Vg over 2, okay, and you square it, it will be Vg squared over 4, and you divide by the impedance. Oh, sorry, it is the current squared times the, it is the current squared times R input. Okay. Okay, and the current is equal to Vg over Zg plus R input all squared. When there is matching, the input signal will be Vg squared over 4Rg. It will be the same. We have already derived this for noise, and it will be the same equation for signal, but we can see here it is. We already derived that. I think here it is. It is P noise equal Vn squared over R. If it is P signal, it will be V generator squared over 4R. As you can see, it is here. It is Vg squared over 4R times M. M is the mismatch factor. It is given by this equation. Now, the noise output power of the amplifier is the noise input from the generator resistor times the gain, power gain, plus the noise contributed by the amplifier. Now, the noise contributed, now this is A, P, and I is given by this equation. We have here, at the output, we multiply this equation here, KT delta F M multiplied by A, KT delta F M multiplied by A to obtain the input noise power from the generator impedance to the output, and then you add the noise power of the amplifier. It is F minus 1 times KT times T naught, because the temperature here is T naught, delta F times the gain. This is the amplifier. We have taken this from here because, as you know, the noise temperature of the amplifier is F minus 1 times T naught. So we multiply by KT delta F at the input, and we multiply by the gain to obtain the power from the amplifier at the output. If we take this as a common factor, AMKT delta F, AKT naught delta F, if we take this as common factor, A times KT naught delta F, this is the noise at the output, refer to the output. Here we will have F minus 1, and if you divide this by this, A will cancel with A, and K will cancel with K, and delta F, but we have here T over T naught, and we will have M here. So this is the noise output power. Now to find the noise figure of the amplifier with mismatch, PSI over the signal power is multiplied by the gain to obtain the output power. And the signal input noise is here. You can see it is KT delta FM. Here it is KT delta FM. And the output is here, is this equation here. AKT delta F naught here, delta T naught delta F times M. We take this here to here. Here this is the amplifier noise at the output. The total amplifier noise, the total noise power at the output. This we take this equation here. This is same equation. So now again we cancel PSI with PSI, and also we cancel A with A here, and K is cancelled with K here, and delta F is cancelled with delta F here. So this will be in the numerator now, and this is in the denominator. We will have here T naught, as you can see in the numerator, times M T over T naught plus F minus 1 here, and this will be in the denominator, T times M, and this is equal to T naught over T times T over T naught. Here you can see if you take T naught over T, or if you want, this is 1. In fact, this is 1. The first term is 1 plus this is T naught, cancels with T naught here, and T with T, and M with M, plus T naught over T here, plus T naught over T, okay, over M. Also there is M in the numerator, in the denominator. We will have here T naught over T, and we will have M, and we will have F minus 1. This is the equivalent So it is T naught over T over M F minus 1. If the mismatch factor is 1, there is no there is complete matching, and if T naught is equal to T, this is equal 1, and 1 will cancel 1, and F prime is equal to F. Now definition here, the system noise temperature, as we divide by K delta F to obtain the system noise temperature. Also just remove K delta F and remove A, because we want to refer the noise to the input. So this is P noise output from here. This is P noise output here. Take away A, cancel A, and cancel K delta F. The remaining is T naught M T over T naught plus F minus 1 is the equivalent noise temperature. As we can see, this is the equivalent noise system temperature, we call it. Thermal noise voltage across the terminals of a passive network if we have a passive network, we use Z input here is R input plus J X input. We use the same equation for the RMS noise voltage as a resistor, but instead of R we put R input. It is for KT no, T naught for KT naught delta F R input volts RMS. Simple. And this is derivation for the same equation, repeated derivation, so no need, we obtain this the same equation. I will stop here and we will continue later on. Thank you for listening.